So like I was saying, we've done integrals and we've done limits. We have not done what are called improper integrals. This is an integral that is approaching like positive infinity or negative infinity or both. So what we basically do is we take, like if an upper limit of integration is infinity, what we do is we basically change this to a limit and then change the upper limit of integration to a variable. And then we evaluate the integral, and then we do the limit of that. Okay. These are just other variations. So this is if it goes to infinity. This is if it's negative infinity to b, then we change it here. And every once in a while, we might have negative to positive infinity, and then we have to split it up into two separate ones. Okay. So if we get a limit at the very end, the improper integral converges, and the limit is the value that we get. If the limit fails to exist, then we say it diverges. In part 3, if either, so remember parts 1 and 2 only have one infinite, but number 3 has two, a negative infinity and a positive infinity. So in this case, if both from the left and the right converge, then the function itself converges. But if either one of those diverges, then the whole thing diverges. All right, let's do this. Okay, and you can probably take a guess if you're looking at this, negative infinity to infinity of e to the x. So we want to first, for part A, we want to express the improper integral as a limit of definite integrals. So first thing, I'm going to rewrite this. Negative infinity to, we could pick any number. I'm just going to pick 0. This is our additivity property, and then I'll have 0 to infinity e to the x dx. Okay, now I'm going to express it with limits. So we're going to say a limit as b approaches, or sorry, I want to make that an a. A approaches negative infinity from a to 0 of e to the x dx. And then I'm going to make this limit as b approaches infinity from 0 to b, e to the x dx. Now that 0 can be any number, right? We could have made it a 1. We can make it anything. It doesn't really matter. Now for b, we're going to evaluate this. So we'll have limit as a approaches negative infinity. So that's going to be e to the x evaluated from a to 0. And then the limit as b approaches infinity of e to the x from 0 to b. Okay. So limit as a approaches negative infinity, so that's going to be e to the 0 minus e to the a, plus limit as b approaches infinity of e to the b minus e to the 0. Okay, so in the first one, now we're going to evaluate the limit. So e to the 0, that's going to be 1 minus, okay, as a approaches negative infinity, that'll be approaching 0. Plus, well, this will be infinity minus 1. So even though, so this is an example where one part of it converged, but the other part diverges. Bless you. All right. So therefore it diverges. Excellent. Okay. Now we want to do 1 over x from 1 to infinity. So the first thing we're going to do is rewrite this as a limit as b goes to infinity from 1 to b of 1 over x dx. That's what I was saying. Like, it's basically stuff that we've already done. We're just combining it. And it's a lot of writing to get to that conclusion, but it is necessary. You do need to show that you're taking the limit. Okay, this one is going to be, so the integral, that's going to be natural log of x, evaluated from 1 to b. So we have natural log of b minus natural log of 1, but that's just going to go to infinity. So this one is also going to diverge. Okay, I promise this one's not going to diverge. Okay, so this one, okay, first what I'm going to do, this is where in this lesson we have to take anything that we've done up until this point to evaluate integrals. So we might think u substitution, we might think tangent inverse or sine inverse, or partial fraction decomposition, any of that stuff. So first thing, I'm just going to rewrite this. I'm just going to put that 3 in front. So limit as b goes to infinity from 2 to b of 1 over x squared minus x dx. Unfortunately, there's no alternative except for to do partial fraction decomposition. So I'm going to go over here. I'm going to do 1 over x squared minus x is going to be, well, if I factor out an x, I can do a over x and b over x minus 1. And we want to figure out the values for a and b, and then we'll pick back up over on that integral. So I have a times x minus 1 plus b times x has to be equal to 1. So if I let x equal 1, I'll get b equals 1. And if x equals 0, I'll get a is negative 1. Okay, so now I'll pick back up over here. So we have 3 times the limit as b goes to infinity from 2 to b of negative 1 over x plus 1 over x minus 1 dx. Okay. I'm just gonna, so 3 limit b goes to infinity of, okay, now I'm going to evaluate my integral. So that's going to be negative natural log of x plus natural log of x minus 1 from 2 to b. Now, I don't need to put absolute value around the x, because if I look at my limits of integration, it goes from 2 to b. So okay. Now, there's a couple ways we could do this, but what I'm going to do is rewrite the inside using my properties of logarithms. So that's going to be, I'm going to have natural log of x minus 1 over x. So remember, anytime it's like a subtraction, right? Now that you don't have to do that, but you could do it later, you could do it before, but I'm just going to plug it in here. I think it's easier. Okay. All right, now we can plug in. So this is going to be natural log of b minus 1 over b minus natural log of 2 minus 1 over 2. Okay, now as b goes to infinity, what is happening here? Well, this whole thing is going to approach 1, right? Because it's the same degree in the top and the bottom. So natural log of 1 will be 0. Does that make sense? Okay. And then we'll get minus natural log of a half. Okay. And that's what we get. Therefore, 2 to infinity, that integral of 3 dx from x squared, or x squared minus x d. Oh, I already have the dx. This converges to negative 3 natural log of a half. They're just lengthy problems. It's not like the actual math involved is that difficult, but it's a lot to remember. So it has like stuff from logarithm, stuff from partial fraction decomposition, evaluating limits. It kind of combines that whole thing. All right. This one, this is going to be a tabular method. It's x times e to the negative x. All right, first thing, I'm going to rewrite this as b approaches infinity from 1 to b, x times e to the negative x dx. Okay, so over on the side, I'm going to do my tabular. So I'll have the derivatives on the left side, the integrals on the right. So that's going to be 1, 0. Negative e to the negative x, e to the negative x, and alternate plus minus. I know it's been a while since we did this. Okay. All right, so we get the limit as b approaches infinity of negative x e to the negative x minus e to the negative x. Let me make sure I got all my signs right here. Oh, why did I put dx? That's supposed to be evaluated from 1 to b. So that will be the limit as b approaches infinity of, I'm going to write this as negative b over e to the b minus 1 over e to the b. And then here I have negative 1 e to the negative 1. So, or sorry, yeah. Right, did I do that? Let me make sure. And then minus another 1 over e. Perfect. Okay. So in the first case, right, now that we know the whole thing about like what grows faster and slower, we know this goes to 0, this goes to 0. And so we just have, that's going to be negative 2 over e, and there's another negative sign, so it's going to be e2 over e. So therefore, this converges to 2 over e. I'm debating if we should do the next one or skip it and come back. Maybe I'll leave some for tomorrow when everybody's here. Yeah, because this is just one more example. This one's going to be a tangent inverse, so. Right, 1 over 1 plus x squared. So I'll just put that here. We'll come back to this one. And okay. So those were improper integrals because they had infinity or negative infinity. But we also have other types of integrals that are improper. And that is if we have a vertical asymptote, right? Yeah. So like if I'm looking at this graph, 1 over square root of x, it is undefined when x equals 0. But I could still possibly find the value of the area, which is kind of crazy because you're like, wait, it's infinite, right? But if we look at the limit, it is going to converge to a value. All right, so that's why we do so if we take this, what we would do is we would go from, instead of putting a 0 here, we would put an a. So we would rewrite this as the limit as a approaches 0 from the right. Because remember, with a vertical asymptote, you can only, when we're actually evaluating the limits, we can only evaluate it from the left or the right. All right, so let's take a look at what happens here. Okay, think of this as x to the negative 1/2. So it'll be x to the 1/2 over 1/2, so 2 root x. Evaluated from a to 1. So we have 2 root 1 minus 2 root a. And as a approaches 0 from the right, we get 2. So therefore, the area under the curve from 0 to 1 is equal to 2. Kind of crazy. Okay, this is just all of it in notation here. So these are just, anytime you have a discontinuity, and like that previous one was a vertical discontinuity, right? So you can split this up however you want, right? It just depends on like which side of the asymptote or discontinuity you're evaluating. And again, if both of them are have discontinuities, you just split it up into 2, kind of like when we were doing the negative infinity to infinity. And then same thing as the last one. Like 1 and 2, it either converges or diverges. For the third one, if one of them diverges, then the whole thing diverges. So both of those have to converge. All right, state why the improper integral, state why the integral is improper. So it is improper because the denominator can't be equal to 0 when x equals 1. So there is an infinite discontinuity at x equals 1. Okay, now we have a situation here because 1 is between 0 and 3. So we have to separate it into 2. So we'll separate it. Let's do Okay, so let's make it, and honestly, you know how I was using A and B? I don't care what letters you choose. A, B, C, it really makes no difference. So let's do the limit as A approaches 1 from the left. So that'll go from 0 to 1. Of the integral. Plus, then I'll do the limit as B approaches 1 from the right. So B to 3. Is that okay? Oh, I just realized I put 1 here. I want to make that an A. Sorry. Okay. Now we'll do the integral. So this is the first. So let's see, that'll be x minus 1 to the negative 2/3. So that'll be x minus 1 to the 1/3 over 1/3, or it's going to be 3. And honestly, both of them are going to be 3. So if you want, you could put the 3 in front and just make this the cube root of x minus 1 from 0 to A. And then this will end up giving us the exact same thing. So cube root of x minus 1 evaluated from B to 3. Okay, so we have a 3 in front of everything. Now we will have limit as A approaches 1 from the left. So that's going to be cube root of A minus 1 minus cube root of negative 1 plus the limit as B approaches 1 from the right of cube root of 2 minus cube root of B minus 1. Okay, well, this part and this part are just going to go to 0, right? So this will go to 0. This will go to 0. So I have a 3. This was, okay, so we subtracted a cube root of negative 1. So that'll just be a positive 1. And then plus cube root of 2. And honestly, we can just leave it like that. So therefore, this special integral here converges to 3 times 1 plus cube root of 2. I think I'm going to skip this next one. This one is actually easier. This one just has a discontinuity at 2. Yeah. Okay. Okay, so I want to do this comparison test and let's just do one of these examples, and then that'll just leave us with like 3 to do for tomorrow. Okay. All right. So sometimes we can't evaluate an integral. Okay, I'll give you an example. Look at the next one. If I were trying to integrate 1 over x cubed plus 1, can't use substitution. I can't use partial fraction decomposition, right? It's not a x squared plus 1, so it's not going to be a tangent inverse. So nothing is going to work here, okay? In that case, we have something called the comparison test, all right? And in the comparison test, the way it works is, let's say you know something to compare it to converges or diverges. So in other words, let's say f of x is a smaller function and g of x is the bigger one. if this one converges, so in other words, if the bigger one converges, then the smaller one converges. And we'll get to the point where like you'll be able to really guess which ones converge or diverge, but that's also something we'll learn in chapter 10. Then if the smaller one diverges, then the bigger one diverges. Okay, so we'll just do this last one here. Use a comparison test to determine whether the integral converges or diverges. Okay, so again, we can't use any other method. So what I'm going to do is I'm going to pick a function that resembles this one in end behavior, that looks really similar. So I'm going to compare 1 over x to the third, because that we can evaluate, okay? And not only that, it's bigger than 1 over x cubed plus 1. Okay. So since we're going to compare it, if we can get 1 over x cubed to converge, then I know this one's going to converge. Okay? Oh. Okay, so I'm going to rewrite it with a limit. So we'll have limit as b approaches infinity. So this goes back to the beginning of the lesson. I'm going to write this as x to the negative 3. Okay, so limit as b approaches infinity, we will get x to the negative 2 over negative 2. So it'll be negative 1 over 2x squared, evaluated from 1 to b. So we'll have negative 1 over 2b squared minus negative 1 over 2. It goes to a half. Okay, so this tells us that 1 over x cubed converges. Therefore, we know the original one, which was smaller, also converges.